Anybody have any homework questions you want me to go over? Okay. Anybody remember what we're talking about right now? Yes, free body diagrams. Very good. Okay, so if we think about the force types in this class, I've written this down a few times, but I think it's helpful to keep this in mind. Here are all the forces or the force types in this whole class. First, there's weight force. That's the force applied to the object by gravity. And besides the weight force, all there are contact forces. So once you deal with the weight, you can find all the other forces acting on the chosen object by just mentally going around the boundary of the object and looking for where the surroundings make contact with that boundary. Okay? So the types of contact forces, there's 3 of them. The first one is the only one we've done so far. That's pushing forces. And you can identify that if you think of surrounding your object in a puffy coat. Where does the puffy coat get compressed by the surroundings? Okay. After pushing forces are pulling forces. And then the last one is friction. And so that's all that we're dealing with in this class. We've talked about weight. We've talked about pushing forces. So now we're going on to pulling. And to identify whether something's a pulling force or not, think, could the contact between these objects be replaced by a cable? And by a cable, I mean like a string or a rope or whatever. And the same basic thing happen between the bodies. So could this contact be replaced by a cable or a string or a rope or whatever? A pulling force prevents the chosen object from escaping. So the same way that a pushing force keeps the chosen object from invading the space of the other object, a pulling force keeps them from separating. So for example, if you had a cart here and it's connected by some kind of coupler to another cart here, and you applied a force of 500 newtons this way, okay? Let's think of the free body diagrams of these 2 bodies. Well, actually, don't think of it as free body diagram yet. Just think about the 2 bodies. Okay, so here's this one. And then over here is this one. And this one has the 500 Newton force acting on it. Now, since we're applying this 500 Newton force to the right, this whole system is going to be moving to the right, okay? The contact between those two bodies is what makes the cart on the left move to the right when you pull on the one that's on the right. You see that? It's not just the nature of that contact between the bodies that determines that this is pulling. If we applied that 500 Newton force in the other direction, then the cart on the left would have to push to keep the other one from getting closer to it. You know what I mean? But since the force is applied that way, it's a pulling force that keeps the one on the right from escaping. That's what a pulling force does. You can also think like, okay, so when you apply that 500 Newton force, both of these two carts are going to go to the right. Would the same thing happen if you replace that coupler with a string? Yeah, as long as the string doesn't break, it would. And so that tells you that's a pulling force. Okay? Okay, so what kind of forces do you have? On this, there's a weight force, like always. And then down here, there's a pushing force on the wheels from the ground. And over here, there's a pulling force. And on this one, the ground is pushing on the wheels. And over here, the coupler is pulling on it. Okay, so what's the rule for the direction of the force? So the pulling force direction is parallel to the cable away from the chosen body. Well, like in this case up here that I drew, there's no cable. So what does it mean parallel to the cable? Well, you can always come up with this pulling direction by imagining that contact is a cable. And then use that, I mean, just intuitively, you can think of how that cable would be positioned. And the force is going to be parallel to that imaginary cable. So let me do these two. Let me give these masses. So let's say that this one is 20 kilograms. And this one is 30 kilograms. And by the way, I drew the weight on that one, but not this one. This one would also have, I'll call this M2G. But okay, let's draw free body diagrams of these two carts. So this is the 20 kilogram. There's a weight force down that's equal to 20 times 9.81. So that comes out to 196.2. We already figured out there's a pushing force from the ground and a pulling force on the right side. The pushing force is perpendicular to the ground toward the chosen body. And then give that a variable name. I'll call it N20. And then on the right side, there's a pulling force. So that's going to be, imagine those two things connected by a string or a cable. That force is going to be parallel to what that cable would be, away from the chosen body. Okay? And I'll label this T for tension, the variable. That's usually the variable name people give, although just like always, it's a variable, and if you want to call it X or Q or something, you can. But I'll secretly be pretty angry. Okay, and then the 30 kilogram. So first there's a weight force. 30 times 9.81 is 294.3. And then there's the 500 Newton force over here. There's a pushing force from the ground. I'll call that N30. Because there's no reason that those two are going to be the same magnitude, so you have to give them different variable names. And then there's the pulling force here, parallel to the cable, away from the chosen body. And I'm going to give this the same variable name I gave this one. And notice that any two objects connected by the same cable and what I'm going to say here is true even if that cable goes through pulleys on the way. So even if the cable passes through pulleys, feel a pulling force with the same tension. I'll say feel a pulling force with the same magnitude. And the magnitude of that force is called the tension. Okay, so let me do an example. So let's say we have an incline and a rolling cart thing on the incline, and that has a mass of 10 kilograms. And then there's a pulley up here at the top of the ramp, and the 10 kilogram cart is connected by a cable over the pulley to a hanging mass. I'll say that one has a mass of 5 kilograms. And we want to draw free body diagrams for both of these. Okay, well, let's do the easy one first. So free body diagram of the hanging mass. The first force to put down is the weight force. So that's a downward force that's equal to the mass times 9.81. So that's 49.05 newtons. And now mentally go around the boundary and look for where the surroundings make contact with this. The only place is the cable. So that's a pulling force, and that means that the force is going to be parallel to the cable. away from the body. And I'll call that T. And now I'll do the one that's on the incline. The weight is straight down. So notice that the weight is not parallel or perpendicular to that incline. The weight doesn't care what things are touching. It's always just straight down. Okay. And that's equal to 10 times 9.81, so 98.1 newtons. Then look for where the surroundings contact the boundary. There's a pushing force from the ramp. So that's perpendicular to the ramp toward the chosen body. I'll call that N. And notice that that weight force and that pushing force N are not parallel to each other in this case, okay? Because the rules are different for how you determine that force. The weight is always down. The pushing force is always perpendicular to the surface of contact toward the body. And then there's one more force, one more place where the surroundings contact the boundary. That's here. That's a pulling force, so it's parallel to the cable, away from the body. And since it's the same cable as this one, we're going to call this the same thing. And if we had called that X, we'd have to call this X. Okay? Anybody have any questions about that? Okay. So that is a pulling force. Let's do a problem. Let me give you a chance to think through this. So let's say we have an incline this way. And we have two objects connected to each other by a string. Let's say this one is 4 kilograms and this one is 3 kilograms. And there's a force applied to this one pulling it up the ramp. Let's say this is 30 newtons. Draw a free body diagram for each body.